Okay, so let's take a look at this first property. Okay, if you have the log with any base, the a just represents any whole number. Okay, a log of any base of 1 is equal to, well, let's take a look at the exponential form of this. If we were to rewrite this in exponential form, we would take our base a to the power of whatever we're looking for here and set it equal to what's inside this log. Well, what number would have to go here in order for this to be true? A to what power is equal to 1? 0. Okay, so what that means is when you take the value log base a of 1 for any base log, it's always going to have a value of 0. Okay, so if I were to say, what is the ln of 1? It would equal 0, right? Again, take your base. E to what power equals 1? The answer is 0. Right, let's take a look at another property. Okay, let's take a look at this scenario. Okay, so if we took a log with where the base of the log and the value in the log are identical, what would this simplify to? Okay, so if you think of the exponential form again, we take our base a to what power is equal to the value inside our log, which is a, and the answer would be a to what power equals a? 1. Okay, so anytime you have the log where the base and the value in the log are identical, it simply has a value of 1. Okay, so if I said log of 10, okay, again, the unwritten base, if I don't put a subscript, it's an unwritten base of what? 10. So you have a base that's the same as the value inside, so this is going to equal 1. All right, what if we have a value inside our log that has the same base, but it's part of an exponent? Okay, so log base a of a to the x. So once again, let's look at the exponential form of this. If we take our base a to what power is equal to the value inside our log, which is a to the x, and what would you get for the value that's unknown here? It's just x, right? And now, the way that we think of this, or the way that we'll think of this instead of this form, is we'll use the following property. It's kind of a shortcut property that relates to this value. If we took our power here, any power in a log, you can move out in front of the log and it becomes a multiplier. So we could move this power of x in front and it becomes x times the log base a of a. Well, what did we find up here that the log base a of a is equivalent to? 1. And so you just get this value x. So all you have to do is move the power out front, evaluate log base a of a, and you're left with the quantity that we just established, x. Okay. All right, so let's take a look at, now, so everything that we're just going to talk about here will be kind of based on these properties along with the following kind of expansion rules. Okay, so here's some other properties or rules, okay, for expanding and condensing logs. Okay, the first is what we just saw right here. If you take, and this applies not just when the bases of the exponent are the same, it applies anytime. If you take log base a of x to some power y, this power of y can still be moved out front. It doesn't have to only be when the base of the exponent is the same as the base of the log. And this will always be true. Okay, and then you also have the following expansion. If you take log of any whole number base and you take a product inside that log, this product or this log can be expanded into an individual log for each factor of the product. Okay, so here we have a factor x and a factor y, so we can split this into, or expand it into two separate logs. Each one will be the same base. but each one will be its own individual factor. So log base a of x, and instead when you do expand this, if the factors are being multiplied, the logs are being added. So log base a of x plus log base a of y is equivalent to log base a of the product xy. If we added a third factor in here, we'd simply add another individual log. Any factors that are being multiplied are going to have a positive number or a plus sign in front of the log. Okay, so this right here is the expansion rule. And there's also an expansion rule for a quotient, log base a of a fraction x over y. Okay, so if you have a quotient, let's take a look at what this would be if we rewrote it as a product. And so if we rewrote this as a product, log base a of x times y, now what would we have to do to the power of y to move it up to the numerator? We change its sign, so it becomes a minus 1. So these are equivalent expressions. X over y is the same thing as x times y to the minus 1. And so now if we use this expansion rule right here, we would get log base a of x plus log base a of y to the minus 1. Well, what can we do with this power? We can move the power out front. It becomes a minus 1. And so really, rather than going through this whole process, we can just use the shortcut rule for this. When you're dividing two factors inside of a log, when you expand them out, any factors that are in the denominator of the fraction in that log will have a negative sign in front of their logs. So this would expand to log base a of x. Since x is a factor in the numerator, it's a positive log. But because y is a factor in the denominator, we'll change that to a negative log base a of y. Okay, so let's take a look at a couple examples of these, just small, short examples of these. Okay, so let's say we took and evaluated the following. Log base 5 of 25 x squared. Okay, if I ask you to expand this, okay, what you're first going to do is you identify how many different factors do you have. So we have a numerical factor, 25. We have another factor with a base x, which is x squared. So we have these two factors. What that means is when we expand this out, it's going to be expanded into two separate logs. Log base 5 of the first factor, 25. Because these are being multiplied in the numerator, the fraction or numerator of this value in the log, there'll be positives in front of the log. The x squared also a factor in the numerator, so plus log base 5 of x squared. And what you'd have to do here is to continue to apply the properties. Hey, what do you notice about 25? Can you express 25 in terms of an exponent with the same base as the log itself? Yeah. Log base 5 of 5 squared. Plus here, this power of 2 can be moved out front. Log base 5 of x. And now this power of 2 can also be moved out front. Log base 5 of 5 has a value of 1. So it's just the number 2 times 2 log base 5 of x. Okay, and so that would be your simplified form. All right, let's take a look at one more example. Okay, what if I ask you to expand the following? Okay, so if we walk through this process, okay, here we have this quotient or fraction inside our log. So when we expand it, each individual factor will get its own log. So we have a factor with a base x. We have a factor with a base 8. Okay, so when we expand this, again, anticipate you're going to have two logs. And let's see what those are. The first one, log base 2 of our numerator. The whole factor is x squared. And our second one is a factor in the denominator, so what sign has to be in front of our log? Negative log base 2 of 8. Okay, and so what you need to do is think, can you rewrite this number 8 in terms of an exponent with the same base as the log? Yeah, 8 is 2 to the what power? Cubed. We can now apply the powers property where we move the power out in front of the factor, or of the log. And that gives us our simplified form. 2 log base 2 of x minus 3 log base 2 of 2. So what is the log base 2 of 2 here? Has a value of 1. So we wind up with 2 log base 2 of x minus 3 times 1, or 3. Okay. Now, if you were entering these online, you would enter them again with subscripts inside square brackets. So log base 2 would be log square brackets around the 2, x, and then minus 3.